Our planet faces unprecedented urban growth and environmental challenges. The traditional city model, sprawling across a single plane, is no longer sufficient. We must now envision and engineer cities that expand not just outwards, but upwards, downwards, and into new frontiers. This is the era of the layered city, a multidimensional solution to population density, resource scarcity, and climate resilience. Each urban layer demands distinct engineering principles, specialized materials, and integrated systems. From the sky to the seabed, these environments present unique obstacles and extraordinary opportunities. We are moving beyond simple verticality to a comprehensive, multi-strata urban design. Imagine urban centers suspended high above the ground, defying gravity and offering new perspectives. These sky cities would feature elevated platforms, supported by super-tall towers or intricate networks of tension cables and carbon fiber trusses. Their structures demand materials like ultra-high-performance concrete, graphene composites, and aerogels for superior insulation. Transportation within these aerial domains would rely on drones, air taxis, and vertical elevators, seamlessly connected by skybridges. Essential systems include integrated solar panels, wind turbines, and advanced rainwater harvesting. HVAC systems would be meticulously designed to manage altitude, pressure, and temperature differentials, ensuring comfort and safety at extreme heights. The primary challenges involve mitigating wind shear, structural sway, lightning protection, and addressing the psychological effects of living at such elevations. Beneath the surface, a different kind of urban landscape emerges. Subterranean cities would utilize excavated caverns, reinforced tunnels, and multi-level zones. Construction would employ self-healing concrete and basalt fiber for structural integrity, alongside geothermal insulation for energy efficiency. Movement within these underground networks would be facilitated by advanced metros, freight tubes, and autonomous carts. Geothermal HVAC systems would regulate temperature, complemented by sophisticated air purification and artificial lighting. Vertical gardens would bring greenery and oxygen to these enclosed environments. However, the immense excavation costs, often exceeding $1 billion per kilometer for tunnels, present significant financial hurdles, alongside complex zoning laws and the psychological impact of limited natural light. The ocean depths offer another frontier for urban expansion. Underwater cities would comprise pressure-resistant domes, floating platforms, and anchored habitats. These structures require materials capable of withstanding immense pressure and corrosion, such as transparent aluminum, titanium alloys, and marine-grade concrete. Transportation would involve submersibles, underwater trains, and surface docking stations for external access. Life support systems are paramount, including oxygen generation via electrolysis, advanced desalination for fresh water, and thermal exchange HVAC. The engineering challenges are substantial, encompassing extreme pressure, material corrosion, potential marine ecosystem impact, and the critical need for robust emergency evacuation protocols. In arid regions, cities must be engineered for extreme heat and water scarcity. Desert cities would feature low-profile, heat-reflective buildings and shaded corridors, often integrating subterranean cooling systems. Materials like adobe, reflective polymers, and sand-based concrete would be optimized for thermal performance. Transportation would adapt to the harsh environment, utilizing solar-powered vehicles and terrain rovers inspired by traditional desert travel. Energy would come from vast solar farms, while water scarcity would be addressed through passive cooling techniques and innovative fog nets for atmospheric water capture. The primary challenges include securing reliable water sources, managing extreme temperatures, mitigating sandstorms, and meeting high energy demands sustainably. While we innovate in new dimensions, the traditional ground layer remains vital, evolving with modular zoning and smart infrastructure. Across all these layered environments, core infrastructure must be seamlessly integrated. Housing will feature modular units and adaptive insulation, allowing for vertical stacking and flexible configurations. Shipping will transform with autonomous drones, underground freight tubes, and hyperloop corridors for rapid material transport. Vehicles will be electric, hydrogen-powered, and terrain-adaptive, with vertical lift systems for multi-level access. Water management will rely on desalination, aquifer tapping, greywater recycling, and fog harvesting. Air quality and climate control will be managed by smart ventilation, geothermal exchange, carbon dioxide scrubbers, and precise humidity control. Recycling systems will employ AI-sorted waste, composting, and material recovery, fostering circular economy hubs. To accommodate future populations, growth strategies will focus on mixed-use zoning, vertical expansion, and transit-oriented development, creating remote work hubs. The costs associated with these visionary projects are substantial. An underground tunnel can exceed $1 billion per kilometer. Sky platforms range from $500 million to $2 billion depending on elevation and load. Underwater domes can cost between $300 million and $1 billion per habitat. Even desert cities require hundreds of millions for water infrastructure alone. Funding models will necessitate innovative approaches, including public-private partnerships, leveraging sovereign wealth funds, and securing climate resilience grants. These investments are not merely expenditures but foundational commitments to a sustainable urban future. Layered cities offer direct solutions to pressing urban problems. Heat buildup is mitigated through passive cooling, reflective surfaces, and underground shelters. Space constraints are overcome by vertical layering and subterranean expansion. Psychological isolation is addressed through biophilic design, vibrant community hubs, and immersive lighting. Resource scarcity is tackled with closed-loop systems, renewable energy, and synthetic biology for food and water production. Regulatory hurdles will require new zoning codes and international standards tailored for these complex, multi-layered urban environments. Looking ahead, we envision super-spine transit corridors, multi-level highways integrated with solar canopies. Floating solar farms will power both underwater and desert cities, maximizing energy capture. AI urban orchestration will provide real-time optimization of traffic, energy, and air quality across all layers. Bioengineered ecosystems, such as coral-inspired underwater farms and desert algae for food, will redefine resource production. Finally, memory cities will emerge, with layered designs that reflect historical land use and cultural memory, creating a rich tapestry of past and future. These layered cities represent not just an architectural evolution, but a fundamental shift in how humanity inhabits and interacts with its environment. They are a testament to our ingenuity, our resilience, and our unwavering commitment to building a sustainable future.